Continuation of Chapter 2, I call it Chem Study, the organization of the course. Now, the course itself is based upon Dalton's atomic theory. And when we look at Dalton's atomic theory, we find the following sequence. Fundamental particles, which is the protons, the neutrons, and the electrons, and those go together in a certain order to make atoms and molecules, atoms and elements. And atoms and elements then go together to make molecules and compounds. Then molecules interact with other molecules, or molecules and elements interact through chemical reactions. And chemical reactions produce one of three things. That's it: solid or liquid or gas. We're not talking plasmas, things of that nature. So there's solid, liquids, and gases. And then you can take a solid or liquid or gas in combination with another solid, liquid, or gas, and you can make mixtures or solutions. So as we proceed into the course at this point, we have defined what matter is, classified matter down to the most fundamental components, that is your protons, neutrons, and electrons. Now we wish to build it back up through this sequence. Then, in essence, we're starting simple and building to, of course, the more complex. The next topic, or the beginning topic really, is atomic structure. Historically, atomic structure evolved through what we call atomic theories or atomic models. And we'll get to those in great detail in the future. But historically, the atomic models included the following four theories. We call it the Thomson, plum pudding model, and Thomson visualized the atom as a spherical positive field and suspended in that field were electrons, like plums in a gelatin type pudding. Well, that did not last long. Along came what we call Rutherford's shell model. And Rutherford determined from experiment that the atom consisted of a very compact, in his thesis, indivisible nucleus surrounded by the electron cloud. Having a positive charge, incidentally, and the electron cloud having a negative charge. And the structure of it was not defined as we know it today. Of course, it evolved, the structure has evolved over years. Our next theory is what we call the Bohr concentric ring model, and this should start sounding familiar. Because it is used extensively in instructional environments and used to explain certain phenomena, but it consisted of the nucleus, and the electrons were placed in orbitals that we call energy levels, and that's n equals 1, n equals 2, n equals 3, n equals 4 is the terminology used. I'm going to put one more, n equals 7. The reason we have 7 rings, that's the largest element on the periodic chart, has 7 rings. Now, we'll explain that shortly and why it has certain things. But this is the concentric ring model, and within the orbitals or energy levels, each energy level had a certain number of electrons, and it was limited to that maximum number of electrons. And then what we call the Schrodinger quantum model is our modern concept of the atom. And this is based upon what we call the wave-particle duality of matter. This led to what we call quantum mechanics, which leads to the description of the electron character in terms of wave mechanics. Wave mechanics is the mathematical foundation for quantum mechanics in it. So wave mechanics is the probability of where the electron is going to be at a certain energy level and so forth. And we'll study that in detail as we get to the appropriate place in here. But what it led to is quantum numbers. That talk about the electron in terms of where it is about the nucleus, its shape of its orbitals, orientation of the suborbitals, its spin, and a number of characteristics that we understand today gives us more insight into how the atom and elements behave. Well, in describing what you need to know from this point forward, we'll use probably very little of the Thomson model and not much of the Rutherford model, a lot of the Bohr model, and a whole lot of the modern quantum model. And so with this, we start taking a look at what we call the structure the atom. Of course, it's, as you know, made up of protons, neutrons, and electrons. The basic structure of the atom was first proposed in its current form by the Thomson shell model. Thomson was the first one to propose a two-part atom. And here we have a nucleus and, of course, the electron cloud. But we expanded that in the Bohr model to what we call concentric ring model. And those are, again, orbitals or energy levels. Now, it was determined in the course of discovery that each energy level was limited to a specific maximum number of electrons. And that is equal to a very simple formula, 2n squared, where n is the quantum number. So when we wish to define the maximum number of electrons that one could put into a given ring or energy level, then we substitute the energy level, like number 1, into the n position, and of course that would give us a maximum of 2 electrons. And 2 is 4, 2 and 4 is 8, so we can put 8 in that one. 2 and 3 is 9, and 2 and 9 is 18, we can put into that one. 1632, 2050, 3672, and so forth. 98. So representing the maximum number of electrons is shown there. Now, as we go further, you'll see the periodic table will evolve around those maximum numbers of electrons, and how a given element is placed within that periodic table revolves around the maximum number of electrons that can be put in a given orbital as we go through this. Okay. Now, of course, the nucleus in itself is composed of the neutrons and protons. And protons, as you probably already know, it has a positive charge, and the neutrons are neutral. And we'll learn, and you learn in the second semester more than this one, is that a neutron is a combination of a proton and electron. They neutralize itself. But that's another story altogether. Now, when we look at the structure of the atom, there's some terms that you certainly need to be aware of. Let's do these again. 1, 2, 4, 5, 6, 7. The inner rings, if you will, excluding the outer ring, are referred to as the core structure. And many of you already know that the outer shell, or the outer energy level, is called the valence level. Valence shell, valence energy level, whatever you want to put it. And when we use these in a practical context, we can simply say, in the basic concept, all chemistry takes place at the valence level. In the valence level, all chemistry occurs at valence level. By gain or loss of electrons in a chemical process. Now, we move now into the periodic table and talking a little bit about it, because we are interested in the structure of the elements from the periodic chart. table. Okay. When we look at the periodic chart, there are three very important components of what we call an element block. Right here, say hydrogen has its element blocks, number 1, helium, lithium, beryllium, boron, carbon dioxide, and so forth. Okay, each element is given its own element block. Within an element block, you have the symbol of the element, its atomic number, and is typically given in terms of a symbol. This is a common symbol, Z number, and the atomic mass, and given by a capital A symbol. So now, some periodic tables give far more than that in a typical table. They can put orbital numbers and shapes and just on and on. The one that you will have attached to your exam is this one. It has those three items, and that's what you'll need to answer the needed question. Now, in order to determine the structure in terms of how many neutrons, protons, and electrons a given element has, we need to start with the symbology. Symbology is, say, some element X, whatever symbology it is. And what we're going to do, and they put them in different places. Some put the atomic number below the element and the mass number above. It doesn't matter where it is. But the way we set it up on this symbology is that the atomic mass goes up here as a superscript left, and the atomic number is a subscript left. Okay? Now, what the object is to determine how many protons, electrons, and neutrons a given element has. Well, it's very simple to do. If you we'll pick carbon, for example. If you look at it, the atomic mass, rounded to the nearest whole number, is 12. And atomic number is 6. Like that. Okay, so what is the number of protons in the nucleus? What is the number of electrons? And I do it this way because it's just a logical progression. And what is the number of neutrons that are in that nucleus? Okay, notice how we have big number over little number in this arrangement, symbology. Okay, that's important later. But the 6 down here is the atomic number. And that is always the number of protons in the nucleus. So, and the number of protons, we have 6. Now, for a neutral element, the number of protons equal the number of electrons. Because it has no charge. You have the same number of negatives if you do positive, so it cancels out to 0. So we can come in here and put a 6 right there. Now, in the number of neutrons, it's important to note, here's a big number, little number. Subtract the little number from the big number, and you have the number of neutrons. That is, the number of neutrons is equal to the atomic mass minus the atomic number. And that's the long and the short of that. So you can go all over the periodic table and pick a number of elements and easily determine the proton, the electrons for neutral, and the proton number. Okay, so if you would take a minute and okay, so as we look at this critically, the first thing was the number of protons. Well, always the atomic number is the smaller of those two numbers, and as of course 12 in this case, 50 in this case, 38 in that case, 92 in that case. So if we're talking about a neutral element, the number of protons equal the number of electrons. And of course that is 12, 50, 38, and 92. Now, when we get into the next part, which is the gain or loss of electrons in reaction to structure changes in the atom, of course, those will change based on where it is in the periodic chart and whether it gains or loses electrons. So those numbers certainly will change. Now, the number of neutrons is big number minus little number. And so that makes this very easy. 12, 118 minus 50, 68. 88 minus 30, 50. That's easy enough. And then 146. So as you get larger in the structure, the number of neutrons increases drastically because of the nature of the nucleus. Positives are very close together, and they would, of course, repel with explosive repulsion, explosive forces. But there is what we call an equilibrium functioning between the protons and neutrons to maintain at least that compact condition. We're not getting into that any more than that detail. But at any rate, this should be pretty easy for you to understand in terms of picking out protons, neutrons, and electrons. Okay? When we look at the periodic table, there's some terminology that you certainly need to be aware of. See if I can find a smaller chart. So, now, the modern periodic chart has filled in all of these. But we can still define what the structure is from the chart and what it means. Vertical columns, as given in there, are called groups. And these are collectively put together because of what we call the periodic law. All of the elements in a given column, as given here, have similar chemical and physical properties. Now, they're not identical, just similar in that, say, all of the elements in group 1 here on the left, as I'm indicating, have a certain chemistry, and they all function in the same way. And group 2 does the same thing. Now, out of these vertical columns, we can find that the periodic law states the chemical and physical properties of the elements are a periodic function of their atomic numbers. So as we look first at the periodic chart, we can see that lithium follows, beryllium follows lithium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then it starts over with sodium, magnesium, and so forth. Well, the numbers of electrons and the way it's structured lead us to the same number of electrons in the outer shell for everything in group 1. Matter of fact, in group 2 and so forth. So we can now look at each one of these groups and determine how many outer shell electrons they have. in for a group. So the group number, like you have a periodic table, and this is called the transition group, right here in the middle. You can see the term transition metals, and then we have main groups right here. So that's one of the things you need to be certainly aware of. Right through here. This set, along with the set on the far right, are collectively known as the main groups. Well, those that are in the middle here are known as the transition metals. And those which are down here, and it doesn't have a specified name, but these are called intertransitions. That's the lanthanide and actinide series down here. Break those out into these four main groups. Main group elements, transition metals, and three main groups, or intertransition metals like that. Now, I showed you the other day that when you're looking at the periodic table, you can divide it into three classifications of elements: metals, nonmetals, and metalloids. So one of the first things you need to understand about this is start with the boron under group 3A and make a staircase the following way. And just bring this through the last two all the way to the bottom down there. Now, the elements that are touching that line are referred to as the metalloids. The metalloid. And to the left, up to the metalloids, we have the metals. Of course, that includes everything not touching the metalloid collection we have. And then on the right, not touching the metalloids, we have the nonmetals. And those are characterized based on their properties and classified as nonmetals. Okay? Now, at this point, also, as we go across the periodic chart, notice that hydrogen being 1, and helium, lithium, beryllium, boron, carbon, nitrogen, in that order, that represents, of course, the organization in terms of atomic numbers. Well, so everything, the periodic law is a series in terms of atomic numbers. Also, it defines the number of electrons. So if anytime we pick out an element in there for the neutral, that atomic number is also the number of electrons. Now that includes the core structure, not necessarily the valence level yet. We'll get to that in a minute. So that's just some things you need to be aware of very quickly here as we move forward. Now, the row itself are called series. And so you see over on the left, this is one series, series 1, series 2, 3, 4, 5, 6, 7. Why is it just 7 rows in there? Here's the reason. So a row here represents the number of rings that element has. For example, elements in row 1 have 1 ring around. Elements in row 2 have 2 rings around. Elements in row 3 have 3, and so forth. And so we put all the electrons in the various rings, 2n squared, if it holds it. It doesn't mean it's going to hold that many. It just means that's how the maximum number we showed a moment ago. So we have these series. Also notice that the inner transitions will fit right here. Notice how one is 56, and then you go to 57. So 56, then you drop down to the lanthanide series, and then in the second one down here, radium, then you drop down to thorium. And you put that in there, and then it inserts back into the, yeah, sorry about that. Anyway, it's just some organization of the periodic chart and some terminology you certainly will be tested on. And so you certainly need to be aware of those. Okay, now, our group numbers. Now, some of the groups have names, what we call formal names, and some groups do not. Okay? We have what we call the main groups, group 1A, group 2A. Those have formal names. These are alkali metals, and group 2A is alkali earth. Notice one word for group 1, 2 words for group 2. Okay? Now, these are derived from the fact that all of the elements react with water to produce what we call alkaline solutions, or basic type solutions, base. Now, groups 3, 4, 5, 6 do not have formal names. But when you get to group 7, and I'm going to put GP on there just for show, 7 and group 8, we recognize those as having formal names. Very important name, especially group 7, are called the halogens collectively. And include fluoride, chloride, bromide, iodide, and acetine. Group 8 are referred to as your noble gases. And, of course, they include the helium, neon, argon, krypton, xenon, radium, radon, and that's enough. You'll have the periodic table in front of you, so you can find that in trouble. Now, what's the significance of knowing the groups? Well, the name is just kind of a academic thing. Just what they're called. Sometimes the groups 3, 4, 5, and 6, even though they do not have formal names, are referred to, say, as the boron group, carbon group, nitrogen, oxygen, fluoride. The reason they do not have formal names is because they are passing through this staircase as you go from top down. So the properties are not uniform from top down. That is, for example, carbons up here is more of a non-metal, and then you go through a metalloid, a couple of metalloids, and then these have metallic properties down there. So groups 3, 4, 5, and 6 all transition from non-metals, metalloids, down through metallic properties. And so, again, that's why they do not have formal names. But when you look at group 1, 2, 7, and 8, they are uniform in their chemistry from top to bottom. And so they are applied formal names. But like I say, people use say carbon groups and oxygen and nitrogen groups and so forth like that, but they're not official in terms of what they're called. That's main group elements. Excuse me. Valence electrons. There. Of course, that's the outer shell. So if we're looking at the elements in group 1, everybody from hydrogen down through francium has one outer shell electron, and so forth. Group 2, main group, has two outer shell electrons. And 3, you can even go down through, and it has 3 outer shell electrons. Regardless of where they are in the electronic structure, they're still only going to have 3 electrons all the way up and down. But the properties, chemical physical properties, change as you go down through 3, 4, and 5, and 6. And group 7 has 7 outer shell electrons. And so it's very important that you understand when you look at a group how many outer shell electrons, because that leads to how each element reacts, whether it gains electrons or loses electrons. And the reactivity of elements this is a generalization rule that you can depend on as far as basic behavior of the element by itself. Elements tend to gain or lose electrons at the valence level, I should say, by path of least resistance. This is formally called the octet rule for main group elements. The operative note here is path of least resistance. Okay, and there's one other thing I need to put in here. Elements tend to gain or lose electrons at the valence level of the path of least resistance to achieve a noble gas configuration. So when we look at a series of elements, let's start with lithium, beryllium, and we'll jump over to boron, carbon, nitrogen, oxygen, of course fluorine, and neon. I'm going to put helium back here, okay? Now, when we talk about this is row 2 of the periodic chart. So each one of these elements has two rings. And according to the 2n squared rule, the maximum number of electrons we can put in that second ring will be 8. Okay, according to the 2n rule I mentioned earlier in the lecture. Now, in the first ring, maximum number is 2, so I'm going to put 2 electrons in here, using the Bohr model. So every element in there has got that first ring full. But as you go across in the second ring, we find that lithium, being in group 1, has 1 outer shell electron. And then beryllium has 2, and boron has 3 electrons, 4 outer shell electrons. 5 electrons, 6, 7, and noble gas 8 electrons. Now, again, the octet rule says that in chemical process, these elements will gain or lose electrons to achieve a noble gas configuration by the path of least resistance. Now, in this, let's take lithium, for example. Lithium has 3 protons and 2 electrons and 1 electron. So the 3 protons are holding on to 3 electrons, right? Okay? So the question is, will the lithium prefer, by a natural process, to lose 1 electron or gain 7 more electrons? So that's the dilemma that you face right now, and it's kind of obvious, but if what happens, will it gain 7 electrons to give the octet or the noble gas, or lose 1 electron to give a duet, which is like helium? Gain and loss to achieve a noble gas configuration. They're either going to gain to the noble gas configuration or lose. Well, considering the fact there are only 3 protons attracting electrons, and if you added to that, say you had 1 electron and, 2 electrons and 1 electron, plus 7 electrons, and you have 8 electrons being held on by 3 protons. Well, that's not practical from a fundamental standpoint. However, if I have a 2 and 1 and lost 1 electron, then the system would have 3 protons holding on to just 2 electrons. And that would be more stable in the context of what we're talking about than would be if I tried to add a whole lot of electrons that didn't have much attraction to begin with. Now, what you want to look at is as we go across the table, periodic table, we're increasing the number of protons in here. Okay? So while we're at 3, we go to 4, 5, 6, 7, 8, 9, 10 protons holding on to the electrons. So, make a long story short, once you get to boron, or 3 outer shell electrons, up to that point, the tendency is to lose electrons. From the beginning of that row to that particular point. Beyond that, the tendency is to gain electrons because you have a larger number of protons in the nucleus functioning to hold on to whatever you need. So this would gain 4 electrons, this would gain 3 electrons, and this would gain 2 electrons. This would gain 1 electron, and of course that's the noble gas anyway. So carbon is kind of the transition, but we use it as a non-metal gaining electrons for the most part. Now we're talking about individual elements by themselves and the process of chemistry here. Okay. How a given set of elements will behave fundamentally is groups 1, 2, and these are metals, but group 3 is where you want to limit your losses. So everything to right up to here, let's see, that's group 3. I'm going to go to 4. Group 4. this group. So everything to the left of this kind of straight line, L-looking line right here, are the metals to start with. And their primary tendency is to lose valence electrons. On the right of that line, are nonmetals, and we'll include the metalloids also. And these tend to gain electrons to achieve that noble gas configuration. So now you have a kind of a generalization of how these elements function in a chemical process, gain or lose electrons. Now, when we talk about the transition metals and intertransition metals, there's it's a term that needs to be understood, but we can't really explain it all right now. When the average, I wouldn't say the average, the number of out-of-shell electrons in the transitions and in the intertransitions range from 1 electron out to 4 or 5 electrons. And all of them are assumed, since they're to the left of the staircase and on the left over here is a collective metal, they will be losing electrons. So some of the next rings in, what I'm getting to, may have as many as 10 electrons, or in some cases 14 electrons. Those are called pseudo-noble gas configurations. So when you gain or lose electrons in the transition block or the intertransition block, the next ring down is not necessarily an octet. Matter of fact, it probably won't be an octet. And we call those pseudo-noble gases, but the terminology is there to express a certain issue going on. It refers to variations in atomic structure.